Greetings all, Ferrari-Man 601 here. Let's try something entirely different. No motorsport, no racing, no cars, no nothing like that, but we are very much talking about the sciences, in particular mechanical engineering and then physics involving things like optics and pressure wave propagation and aerodynamics and a little bit of ballistics as well. What you're seeing on your screen right now is the fiery liftoff of SpaceX's Falcon Heavy launch vehicle, and this flew yesterday morning from Cape Canaveral, the Kennedy Space Center that SpaceX has leased a portion of Launch Complex 39 from. And here we are, that onboard shot from Falcon Heavy. It's only the fourth time that SpaceX have flown their highest capacity orbital launch vehicle, simply because the demand for these really heavy payloads just isn't there for SpaceX for the moment. But Falcon Heavy, it's gone 4 for 4 in terms of its success rate, and there you see what a majestic sight that is, climbing away into the no longer foggy sky there yesterday morning over Florida. Of course, those of you who follow SpaceX are undoubtedly more familiar with the Falcon 9, which they fly much more frequently than Falcon Heavy, but Falcon 9, effectively we have 3 of those strapped together here to form the first stage of Falcon Heavy. And of course, the first stage of Falcon 9 being entirely reusable, all 3 of these stages here, these core boosters effectively, are in theory reusable, though that didn't happen yesterday here for Falcon Heavy. But just as we passed maximum dynamic pressure here in this launch of Falcon Heavy, did you see it? Did you happen to catch anything interesting there? A very interesting visual phenomenon happening around the base of those engines, right where the plume is starting to lick up along the sides of the strap-on boosters there, as it were, here on Falcon Heavy. If you didn't, that's what this video is all about. So initially, just to get our orientation here with respect to the orientation of the vehicle relative to us as the observer, as well as the phase of flight that we are currently in during this launch profile. We are about 75 seconds into flight here. We have just exceeded the speed of sound, and the vehicle is now in the area that they refer to as max Q, or maximum aerodynamic pressure. This means that the structural stresses exerted by aerodynamic loading on the vehicle are the highest that they will be during the launch phase. And obviously the vehicle is going to be really pushed toward its design limits here, and it's happening because we have interesting aerodynamic phenomena going on. We are in this transitional zone between subsonic and supersonic flight. We have exceeded the speed of sound locally relative to our altitude. Remember, as your altitude goes higher, your air density, your atmospheric density drops, which means that things like the speed of sound, for example, are going to change. The speed of sound at sea level is much faster than it would be at, say, 30,000 feet or 50,000 feet. And as we go higher, the speed of sound continues to get lower until we effectively have no speed of sound because there's not enough atmosphere to transmit sound waves as we know them. So that's something important to remember. Remember, we also express the speed of sound as a function called Mach. So Mach 1 being the speed of sound locally, depending on our ambient pressure and ambient temperature, things like that. We're talking around 1,100 kilometers per hour in terms of the speed of sound at sea level, assuming standard atmosphere. So that is around the speed that Falcon 9 has achieved at this point, and of course we are continuing to accelerate hard the whole time because those engines are not letting up for anything. We are at the aerodynamic boundary between 3 very different types of flow as well. We are experiencing, in some areas of the vehicle, subsonic flow. In other areas, we are in transonic flow. So that is flow that is around Mach 0.9 to Mach 1, and then supersonic flow, which is Mach 1 and above. So all 3 of these types of air, the different flow rates, the different relative velocities of air, they are all either directly impinging upon or are immediately in the vicinity of the vehicle at this point of maximum aerodynamic pressure. And different areas of the vehicle will be experiencing different types of flow and the associated loadings therewith. So that's why we call this maximum aerodynamic pressure. That is the situation the vehicle is in right now. The next sequence of images are all sequential. So as we look at each successive image, we are moving forward in time. The vehicle is continuing to gain speed and altitude with each successive image. And on this next shot here, again, we have moved forward in time relative to the previous shot. The vehicle is still in basically the same orientation and relative attitude compared to where we are observing it from. And obviously, again, we're in that max Q period. However, as we start to look down the side of the vehicle toward where the engine nozzles are and we see all of this glorious exhaust flame, do you see anything starting to crop up here, visually speaking? Now, I'm not referring to the apparent impingement of flame up toward the side of the vehicle. This is not what I am concerned with. This is a function of ambient pressure. Again, as we go up in the atmosphere, the ambient pressure drops, the air density is dropping, therefore, and because we have this exhaust gas, which obviously is bursting forth out of these engines at extremely high pressure, there is less and less of an ambient atmosphere to constrain that and give that stereotypical teardrop shape to the exhaust. So as the ambient pressure decreases, the exhaust is going to want to expand much more readily into a roughly spherical shape behind the vehicle. And of course, you're going to start to see impingement of that flame along the sides of the vehicle. This is something that we saw on Space Shuttle, something that we saw on Saturn V. Actually, if you're familiar with the Saturn V, right toward the end of the first stage burn, which actually is pretty similar in duration to a Falcon 9 first stage burn, you had flame impingement at times almost halfway up the first stage of Saturn V. But that is not what I am talking about here. I am talking about another optical phenomenon here, and it is truly an optical phenomenon. It is not something that is physically occurring, but it is still a function of relative air pressures and relative air densities. Do you see anything starting to crop up here? Obviously, as we start to zoom in on this image, the resolution drops, but do you see anything starting to crop up here? Right around the base of the rocket, just above the engine nozzles. If you don't, that is okay, because we've got more shots that'll be more illustrative of this in due course. But there is something already starting to crop up here that should be grabbing our attention. And here on this next shot, you can definitely see in this section, we are seeing something a little bit odd. We take a look right here, cover it over with this line, we are definitely seeing a linear structure that has started to propagate here around the base of the vehicle, just above where we can see the exhaust exiting from these engine nozzles. What is this? It's rather interesting. What I will tell you off the bat, it is not something that is physically there. This is not flame. This is not some piece of the vehicle that has come off. It's not debris of any sort. And it's obviously not some sort of an object that is flying alongside the vehicle here. It is an optical phenomenon that we are seeing, but it is not something that is associated with the camera. It is not something associated with the video, so we're not seeing a technical fault on the camera. This is not lens flare. This is not something going on with the encoding of the video from which this still image is taken, and it's not something that's wrong either with my video encoder, and it's not something that's wrong with the screen on whatever device that you're watching this video. This is something that is physically occurring, but it is not a physical object in the sense of it's not something that has any appreciable mass. It's not something that you could reach out and touch. This is strictly light that we are seeing here. But it is caused very much by the physical presence of the air around this vehicle. Remember, we were talking about the three principal states of the airflow around this rocket right now, the subsonic, transonic, and supersonic flow. It all has to do with this optical phenomenon that we are observing. And on this next shot, you can see that we still have the same optical area, the same phenomenon that we observed in the previous shot, but again, we've moved forward in time, and you can see that relative to its last location, which was right about here, it has since migrated down in frame and is now right here. So that is interesting to note. Between these two images, we have passed maybe half a second. This happened very quickly in terms of real time, but in that half a second, the vehicle has continued to gain altitude and it has continued to gain speed. Therefore, we see that this area of optical distortion has migrated down relative to the relative location of the vehicle. Remember, it's all relative locations here. It's relative velocities and it's relative locations and relative angles because we have to consider the angle from which we are viewing this. This is also very important in terms of the aerodynamics going on because there's all sorts of things going on here with Mach numbers and critical Mach numbers and angles and all sorts of things. And these are all measurements that are going to be affected by location. And they will differ relative to the vehicle as well as relative to each other. So things to consider. But apparently, from what we are observing here, we had a migration in this line from about here now to right here in this image. So interesting to note. But what is actually going on here? Okay, it's all well and good. We found an optical illusion in a rocket plume. What is this? And is this something, first of all, that we can localize to this one event? Is it something that we could even localize to Falcon Heavy? Or do we have further evidence for these things occurring throughout time? Well, we've been flying rockets for about 80 years, all things considered, but it's only really within the last 30 years that we've started to get camera technology that is sensitive enough and high resolution enough to be able to pick up on things like this from rockets in terms of watching them fly, these long-range tracking cameras. As they continue to gain a lot of speed and a lot of altitude, obviously they get farther and farther away, and their closing distance, as it were, they start to open up that distance exponentially more quickly as they get farther along in their ascent. So it's only somewhat recent, again, really within the last 30 years, that we've got cameras that are sharp enough to see things like this. But have we seen things like this before, and not just in November of 2022 with this fourth launch of Falcon Heavy? Let's see if we can find any evidence of this in the past. Right, so let's take a look back in time, shall we? What you're seeing on screen right now is the launch of Space Shuttle Atlantis on STS-104. This was a space shuttle mission that launched on July 12th, 2001. Obviously, you can see a pre-dawn launch, and with booster ignition there, a huge Wilson cloud there. That is also an aerodynamic pressure-driven phenomenon caused by, well, in this case, supersonic flow from the solid rocket boosters. But that's not what we're interested in. Obviously, Atlantis going through the roll maneuver here. You can see a little bit of a wingtip vortex there from the right wing away from camera. Similar weather conditions in terms of winds and perhaps temperatures. That's just a guess on my part, but you could see at launch there, a vehicle sitting on the pad, the clouds generated by the cryogenic fluids venting from the vehicle. They were hanging around the vicinity of the pad, so calm winds, no fog at this point. We did have a lot of fog from Falcon Heavy's launch, but calm conditions at sea level. You can see here we have got some clouds generated here, these vapor cones generated by the aerodynamic surfaces. This is something pretty commonly seen on shuttle launches as the vehicle passed through Mach 1. But also, keep your eyes near the main engines. Those are the three engines arranged in that triangular pattern near the center of the screen there. Have a look. You can see these linear structures that are now passing through the center of the frame, and they're just dancing all around, even in multiple directions, down and up relative to the orientation of the vehicle. You can also see, much like we saw on the shots of Falcon Heavy, they are taking on the colors and relative light levels of the exhaust plumes behind them. Obviously, you've got the two solid rocket booster exhausts. Those are the much larger and brighter flames, and you can see the three main engines there at the tail of the vehicle. They are burning away. And we have got these linear phenomena that are just dancing all around in the frame. They clearly passed between us and the vehicle. They appear to be in front of the vehicle. Another wave of them just went through there. They're taking on the ambient colors of the exhaust plumes, which appear to be apparently behind them. And they are here on this 2001 launch of Space Shuttle Atlantis. So this is not something that we just saw for the first time on Falcon Heavy in November 2022. Here we have great documentation here in HD, very rare for 2001, of the same phenomenon occurring associated with a space shuttle launch. So what is going on here? And before our little inquiry, did anyone notice this before? Has there been any discourse published about it? Well, yes, there has been. Let's take a look at some of that. Well, here we go. I saw all of this happening here initially in my days being a space aficionado observing the space shuttle program. And I saw this phenomenon occurring on many a space shuttle launch, and I had always personally chalked it up to being some sort of aberration from the camera because it just didn't occur to me that perhaps what I was seeing was actually happening. I thought perhaps it was just some sort of issue either brought in by the camera technology itself or some sort of interference in the broadcast, maybe something that was associated with the sound or the extreme light levels associated with seeing rocket propellant burning like this. But no, we're actually looking at something real, and this is a January 2011 paper published by NASA's Marshall Space Flight Center by J.M. O'Farrell and T.J. Rehoff. They're writing about this, and they're talking about how you can take a look at these shock phenomena associated with the space shuttle as it's flying in the transonic regime, and how you could start to deduce some information from it relative to the vehicle's speed, attitude, ambient conditions aloft, winds aloft, things like that. And of course, the manner in which we're gathering this data via the camera technology that was available. This paper also associated with an experimental program utilizing a WB-57 aircraft to image the space shuttle in its first 90 seconds or so of flight, flying on the solid rocket boosters. They would be having an aircraft flying at high altitude around 50,000 feet with high-resolution tracking cameras aloft on board the aircraft to be imaging the space shuttle in flight from the air. So initially looking at the flying space shuttle, looking down at it. So that's a very interesting perspective. And they did this on a handful of flights post the 2003 loss of Space Shuttle Columbia. NASA was very interested in gathering imagery of the space shuttle post Columbia because, of course, we know that the major contributing factor in the loss of Space Shuttle Columbia was damage that was sustained to the left wing, the leading edge of the left wing, caused by insulation foam that was shed from the external tank. It impacted the leading edge of the Space Shuttle orbiter's left wing, and it destroyed the thermal protection system in that region of the vehicle, which ultimately led to it to break up on its return to Earth during re-entry in 2003. So NASA was very interested in this. They're interested in imaging the space shuttle during launch, and it led them to sponsor this work by Rehoff and O'Farrell, and they published it from the Marshall Space Flight Center in January of 2011. What are we talking about here? Obviously, we are taking a look at two primary sources of data. We are looking at the Space Shuttle Vehicle WB-57 Ascent Video Experiment Imagery. So that's the aircraft that was flying with the long-range cameras there, imaging the vehicle in flight, as well as ground camera imagery there, such as what we were looking at both from Falcon Heavy as well as from, in this case, Space Shuttle Atlantis. We are looking at shock boundaries. So what we are seeing here, we have shock boundaries. We are talking about when they appear, so their order of appearance. We have refraction. So remember how we observed that these phenomena, whatever they are taking on the relative colors and brightnesses of exhaust plumes in their vicinity. And we observed, particularly looking at Atlantis, that they appeared to be manifesting themselves between the observer location, so the camera lens, and the vehicle itself. So we're seeing refraction. That is a bending of light here caused by the appearance of these phenomena. What are we calling them? We're calling them linear optical distortions right here, and they have something to do with shock boundaries. So what are we doing? We've got all kinds of things here. The case studies that these two authors are looking at in predominant order here, we have STS-114, which was a flight of the Space Shuttle Discovery in 2005. That was actually the return to flight for the Space Shuttle program after Columbia. Again, NASA very interested in this imagery post-Columbia, and STS-114 was the first flight. STS-110 was a 2002 launch of the Space Shuttle Atlantis. I believe it was actually the next flight of Atlantis after STS-104, which we just looked at. So we've got these two launches here, two Space Shuttle launches as case studies. And we have two primary manifestations of this transonic phenomena. We have got, on STS-114, we have got shock collar formation, the condensation collar that they call it here. And then we have shock from STS-110. So we have condensation from Space Shuttle Discovery, and we have shock, in other words, linear optical distortions from Space Shuttle Atlantis on STS-110. They go on to discuss a shock sheath from STS-110, and they also go on to talk about these LODs, linear optical distortions, themselves and the effects that they have on the visual appearance of the space shuttle vehicle as it is climbing out. We also go up to STS-116, which I believe was another flight of Discovery, and we even have STS-107. This was the accident flight of Columbia, not associated necessarily with the accident itself, but incidentally noticed there on some of the post-launch imagery analysis from Space Shuttle Columbia on its last launch, STS-107. Here on page 11, we're looking at STS-114 and the condensation collars that we can see right here. This is something that they are pointing out, and quite clearly you can see that we have got these areas here of the condensation that is forming around the vehicle. We saw that as well on STS-104 from Atlantis. Shock boundaries. These are things that we are not quite seeing in this particular view from the ground, but we are in fact seeing this. All of these brighter areas that we can see here, these are all shock boundaries. And what we mean by shock boundary here, remember when we were talking about Falcon Heavy and we're in this flight regime of subsonic, transonic, and supersonic flow. Look at this. MET means mission elapsed time. We're at 50.87 seconds mission elapsed time. Falcon Heavy, we were looking about 75 seconds. The Space Shuttle accelerated a little bit faster than Falcon Heavy, so we are transonic here on the Space Shuttle. We are at maximum aerodynamic pressure on the Space Shuttle here at about 51 seconds mission elapsed time. And look at what we have. We have got shock structure. We have got shock boundaries going on around the Space Shuttle Discovery at this time. 52 seconds into the flight, you can see we have now got a shock angle that is starting to manifest here. And we have got all of these shock boundaries that are evident in all of these sections. Have a look. They are just all over the place. What is going to be the side effect here of all of these different linear areas associated with the different states of the airflow? Well, we're going to start to see linear optical distortions. Just project your mind's eye here for a moment and just look at any one of these lines here that you can see either by eye or some of them that I'm trying to highlight here in this document. What's going to be the effect if we start to look through them up at the vehicle from, in our case, a ground-based tracking camera? We're going to be seeing this boundary, and it's going to be affecting the images that we see from behind them, as it were, right? So as the vehicle continues to accelerate, now at 55 seconds mission elapsed time, you can see just how intricate these structures are becoming and the effect that they're having on the background imagery. All of this back here, the white area to the side here, the left side of the space shuttle stack as we're accelerating, that's a cloud in the background. And it doesn't look like any cloud I've ever seen. It is all chopped up, and you can see some very exaggerated distortions here in the upper areas of the frame here. That is due to the relative pressures and relative densities of the air as it is being displaced here by the space shuttle as it's punching through it now at pretty much supersonic speeds. We continue here at 59.72 seconds mission elapsed time, and you can see now we have got this shock shape that has started to manifest as it's starting to cloak the vehicle here. The space shuttle is truly supersonic at this point, and you can see the principal structure that we've partially highlighted, the nose cap of the external tank punching this hole through the atmosphere. You can see that we have got these structures emanating from the nose caps of the solid rocket boosters on each side. Obviously, the left side solid rocket booster is most visible to us here. You can also see that we have got waves coming off of the field joints of the solid rocket booster. These are the segments of the motor that would be assembled at Kennedy Space Center in the field, hence they're called field joints. And you can even see the orbiter is casting these distortions, these lines of distortion all the way through. So we have got multiple sources of these lines that are emanating from every major structure on the space shuttle. Basically, everything that is presented to the airstream is going to be casting this aerodynamic shadow, as it were, this aerodynamic shock wave at this boundary between subsonic and supersonic flow over the vehicle. So that's what we're seeing here, and it is awfully cool to see that these researchers here from Marshall Space Flight Center looked into this, and they noticed this from the post-launch analysis of the launch imagery from STS-114 in this case. Again, the purposes of these images was to look for debris coming off of the external tank and impacting the space shuttle orbiter. But the side effect was so very interesting in that we can see aerodynamics at work here, particularly transonic aerodynamics at work. It was so rare to see even in the wind tunnel environment, because in wind tunnels, particularly with scale model testing, it's so difficult to achieve transonic or supersonic flow in the laboratory. So really the only options that we have to study this on flight vehicles is to fly them. So we're seeing this here on the space shuttle, which is really, really cool. And they go into their commentary here. Condensation collars first observed to form at the forward areas of the solid rocket boosters, external tank, and orbiter at about 41 seconds mission elapsed time. So these were the vapor cones around the nose of the orbiter and the nose cones of the solid rocket boosters. The condensation collars result of pressure change at the shock boundary. We're going into an area of low pressure. We've got the highest pressure right at the nose tip, and then as the air expands around the aerodynamic surface of the solid rocket booster or the external tank or the orbiter cockpit area, the air, it needs to expand to pass around that. When air expands, its ambient pressure drops. So any moisture that's in the air is going to condense and form a cloud. So that's what's happening here with the condensation collar. Given sufficient humidity, condensation of the available moisture provides a visible counterpart to the acoustic shock wave being generated. Depending on atmospheric conditions, the condensation collars typically form just prior to the vehicle attaining Mach 1. For STS-114, the Mach number was about 0.95 when the condensation collars were first observed to form. As the Mach number increases, the shock angle to the vehicle becomes more acute. The bow shock and the structure of the secondary shocks from vehicle protuberances are clearly visible, and that is figure 7. So figure 7 that we highlighted all over the place, vehicle protuberances, that is things like the field joints on the solid rocket boosters, things like the payload bay door seams on the orbiter, things like even some of the gaps between some of the thermal tiles on the orbiter, things from the orbital maneuvering pods on the orbiter. These are all incongruities in the vehicle structure, and they will generate their own shock boundaries, and we're seeing that here. And that's giving rise to the intricate structures that we're observing. Remember on that STS 104 video where we were seeing these shocks going in both directions? That's why we're looking through different areas of this cone as the vehicle gets higher and farther away from us. And that's what it gives them that apparent scintillation effect. That's really, really cool. Section 3, they get into space shuttle vehicle ground camera imagery, in particular camera E207, which is exactly the same shot that we were looking at from STS-104, and quite similar to the shot that we were looking at from Falcon Heavy. It is at the Playa Linda Beach area, just north of Kennedy Space Center, and the shuttle flew from this area, basically the same area, if not exactly the same launch pad as Falcon Heavy, so very similar in terms of our viewing angle. You can see the trajectory here of STS-110 in this case, very similar to what we saw in STS-104. They were both flights to the International Space Station and both launching from the same point on the planet, so very similar trajectories, you would imagine. They get into the narrative here in terms of when they're able to observe shock boundaries. They are saying here the initial observation of a shock boundary is dependent on the location of the camera relative to forming the shock cone, and other ground cameras may initially observe shock boundaries at a time different than that of camera E207. So as we were talking about prior in terms of relative locations, very important. because we're seeing a real phenomenon, but we're not seeing one that's uniform relative to an observer. It's uniform relative to the vehicle, but it's not uniform relative to the observer. What we see here from STS-110 looks very similar to what we saw from STS-104. You can see that we have got these linear optical distortions here at 59 seconds mission elapsed time, and then 59 and 2/1000 seconds mission elapsed time. You can see what's going on with this. You can see how the optical distortion is taking on the relative brightness and color of the vehicle exhaust plumes in its vicinity. In particular, you can see the center main engine here on the Space Shuttle orbiter. It is casting its color into this linear optical distortion. Very, very cool to see this documented so clearly. Here we can see multiple shock boundaries going through the main engine, and you can see the refraction here. Have a look at what's going on. Obviously, this is a circular engine nozzle, but you can see just this exaggerated profile as the shock boundary is crossing it relative to our observer location. You can see what it's doing to the light. It is completely distorting the appearance of the Space Shuttle main engine nozzle. Really, really cool to see that. And there's an even more dramatic shot as we continue to move on with this. The body flap, which is an aerodynamic control surface below the main engine nozzles on the Space Shuttle. Have a look. It looks like it's been cut in half. This is a single piece. This is not bifurcated in any way. When it deflects all at once. It's one piece. It appears to be cut in half optically here by the optical illusion that is occurring. And obviously there's a lot of refraction as well visible on the, in this case, the left-hand main engine nozzle. But that is really, really remarkable to see all of this stuff here documented. Here we can see the viewing angle relative to mission elapsed time for STS-110. So it appears that we have got an optimal viewing angle here in terms of when we can start to see the shock boundaries of about 48 degrees. And you can see as well mission elapsed time as we go on. Starts to become apparent at around 56 seconds. Very cool. Here we get into, I believe these are MATLAB simulations, talking about the propagation of the overall shock cone. Remember from STS-114, looking at these images here, this is the shock cone that we're talking about. Coming back down, you can see what's going on here. E207 is not going to be seeing the boundary layer yet between that ambient pressure flow, that subsonic flow, and then the transonic and supersonic flow at the boundaries of the cone and then within the cone itself. Once E207 starts to view perpendicular to that, we start to see, again, 55 seconds mission elapsed time, and then eventually we're looking directly through it here at about 60 seconds mission elapsed time. So that's where we start to see the distortions in the main engine nozzles, and then of course we have an aft view here looking at the vehicle as it's climbing out at 60 seconds mission elapsed time, E207 looking straight through the shock structure, again, that was so apparent on the imagery from STS-114. So that is accounting for what we're seeing on Falcon Heavy, as well as what we did see on the Space Shuttle. They get into their analysis section where we're getting into order of appearance and things like that. Not really important in terms of what we're trying to do here, just to demonstrate that, yes, this exists and this is why it exists, and it's really, really cool that it exists. But they get into all of these different parameters that are noted here. The first lot is noted at 55 seconds mission elapsed time. A late occurring lot often appears and travels aft at 60 seconds. So that's really cool. You can see that they're not only constrained to the areas of the engine exhaust plumes. We have one here on Atlantis STS-110 that is appearing to cut through the right wing of the orbiter. It's just not quite as easy to see because they're not refracting the really bright light from the engine exhaust plumes. Amount of refraction due to density differences on opposite sides of the shock boundary. So density differences on opposite sides of the shock boundary. What's happening here is the refractive index of the atmosphere is changing due to relative densities. This is something that you can see even with your classic hot road mirage. Obviously, the warmer air is going to be less dense than the cooler air, so that hot road heated up by the sun, you're going to get a reflection in many cases, or a refraction in some other cases, where something in the distance appears to be stretched out and then sort of reaching down into the road surface from time to time. You've all seen this on a hot road. That is due to differences in air density caused by temperature in those cases, but here it's caused by ambient pressure between subsonic and supersonic flow. So we are seeing refraction here caused by pressure changes. That's really, really interesting. Back here, you can see, once again, we have got that refraction of the main engine nozzle, and you can see, again, that apparent bifurcation of the body flap. Multiple ones here again from STS 110. Visible here, we saw exactly the same thing on STS 104. And ripples in the shock boundary, again, we saw this on STS 104. And we saw this quite late in ascent as well, all the way up toward SRB SEP. Here they noticed that as well on STS 107. STS 116 are these shots. STS 107 is the next shot. Just as we observed on 104, you can see the main engine exhausts. They are being refracted down here in Figure B. Figure A, where you have refraction of the SRB plumes. Shock boundaries here on STS 107. This is Space Shuttle Columbia's last launch. Debris being noted here. This is the debris that impacted the orbiter's left wing and caused the terminal damage to the vehicle. But again, they are illustrating shock boundaries. Very interesting. Very interesting indeed. And again, this is something that was not really intended to be a finding of the imagery that was ordered by NASA in the wake of the Columbia disaster, but it was something that was very interesting to be noted, and again, interesting enough that Marshall Space Flight Center allowed a paper to be published about it. And yes, it is a real phenomenon, and it's something that if you were looking closely at the launch of Falcon Heavy, you would have seen. Is it something, though, that is only restricted to rocket flight? It is actually not. We'll show you another example of this. Now for the ballistics connection in all of this little discourse here. What you're seeing now is a picture taken from the forecastle deck of the Iowa-class battleship USS New Jersey. Judging from the superstructure there, this would have been either 1968 or 1969 in her Vietnam-era deployment. However, what you're seeing here is you are seeing the firing of what appear to be the starboard and port barrels of turret 1 in the New Jersey's primary battery, the 16-inch Mark 7 guns, 50 caliber 16-inch rifled guns that were installed on all the Iowa-class battleships. These guns, depending on the projectiles that were loaded, the armor-piercing Mark 8 projectiles, they weighed 2,700 pounds. That's 1,225 kilograms, and they had a muzzle velocity of about 762 meters per second. That's 2,500 feet per second. So that is well supersonic, comparable to, in more civilian terms, a 7.62 rifle cartridge, but this weighs 2,700 pounds versus, what, 160, 170 grain. So, yes, absolutely enormous. But we are talking about something that is flying through the air at supersonic speed, and it's being propelled by a rather large explosive force. So what you can see here is not necessarily the shells that are flying off. That's pretty cool in its own right. You're seeing the two shells from the two apparently simultaneous firings of those port and starboard guns, but you're seeing the expansion of the burning propellant cloud behind those two shells. And what I'm trying to observe with this shot is I'm trying to show you what's going on here in terms of the expansion of a shockwave and its interaction with the atmosphere. Obviously, the shockwave coming out of the gun here, just as the shockwaves generated by a flying spacecraft in these cases that we've been talking about, it's going to be spherical, but it's going to be deflected either by ambient pressures in terms of relative velocities or the ambient pressure of the atmosphere. We've seen how the shock boundaries are compressed into a cone shape by the forward velocity of the Space Shuttle and the Falcon Heavy. But here in the expansion, both from thermal expansion as just from ambient pressure expansion from the firing of a gun here, you can see that this muzzle flash, as it were, it's forming a spherical shape, yes, but it's being compressed almost immediately from the top, bottom, and from our perspective, the front and back, right and left sides. Really, we're talking about a spherical compression here of what would be, in a vacuum, a spherical expansion zone. This is all due to ambient pressure giving us this donut-shaped, almost toroidal appearance to the muzzle flash, the expansion cloud here of the residual burning propellant as those shells have now exited the muzzles of both of those guns here aboard USS New Jersey. But this is a spherical expansion, and it's exactly the same as the shock waves that are generated from an aircraft flying basically at any speed, but it really comes into play here as we approach transonic velocities, as the shock waves start to intersect with each other. And that's what causes the observed sonic boom. When a supersonic object, or in this case an aircraft, passes an observer and its wake, its acoustic and aerodynamic wake, comes across the observer, that's the sonic boom. But it's emanating in these spherical shapes, which then get truncated due to compression into a cone, due to the aerodynamic forces as the vehicle is flying forward. And on this next shot here, another shot of the USS New Jersey firing her main battery. You can see here, though, if we look at the water surface, you can see the depression that has now been formed in the surface of the water by the firing of these guns. Again, it doesn't look like we're firing a full broadside here. We obviously have 3 turrets with 3 guns in each. It appears, once again, that we are firing port and starboard guns from each turret. But in particular, from the rear turret here, the aft section of the ship, you can see this circular depression, the semicircular depression in the water to the port side of the ship. This is showing that spherical expansion of a combination of what's really pressure, but it manifests to us, to our bodies, and to our ears as sound. So you're seeing the sound, the shock wave of the firing of that gun manifesting itself via its effects on the water surface there, and you can see the depression that is forming. So that's what's going on here with a rocket in flight as well, but rather than the firing of naval artillery, we see the shock waves coming from the rocket being truncated and compressed into that conical shape, once again due to the forward velocity of the vehicle through the ambient air, causing more disturbances and causing everything to collapse into a cone. But left to its own devices, you would get this circular irradiation sort of pattern from the acoustic energy and just from the energy that is being released by this vehicle acoustically, and of course the aerodynamic forces they're being truncated, of course, due to the velocity, but this is ultimately what's happening here. So the forward velocity of the incoming airstream relative to the vehicle compresses everything into that cone shape, and it's the interaction between the different areas of pressure within and without that cone, the boundaries of the shock cone itself, as well as other boundaries from other protuberances on the vehicle that generate their own shock boundaries and aerodynamic shadows. It's the interaction between those two things that creates these linear optical distortions. That is really, really cool. So that's what I have here for you today. Just something that I quickly took note of watching the live webcast of the launch of Falcon Heavy, and I just noticed those linear optical distortions, and I remembered all those years ago watching launches of the Space Shuttle. I even remember that launch of STS-104. I remember it launched at 5:04 in the morning my time, and I got up and had my VCR all set to record it. Such was my level of being an absolute geek in my childhood, and I guess that has basically continued to carry through to today. But I noticed that and I said, you know what, that's really cool. I know what that is, but other people, if they even saw this at all, I bet they might be wondering, huh, what exactly is that? So I thought that I would lend my 2 cents on what's going on here and perhaps direct you to some more information about these linear optical distortions and other aerodynamic optical phenomena, which I think are really cool. There have been some great pictures lately, particularly from Falcon 9 launches, simply because they tend to be the most frequent space launches these days, where we're not only looking at aerodynamic effects, but we're looking at acoustic effects. There's this great sequence of images that I have seen. I can't remember the photographer's name at this time, but he has taken pictures of Falcon 9 in early ascent against the sun as well as against the moon. And in particularly in the shots against the sun, you're able to see linear optical distortions, yes, but they're caused by the acoustic shock of the exhaust of the rocket. Again, the rocket exhaust itself is supersonic, so you are seeing this Mach cone phenomenon, but it is being caused by this cloud of combustion products from the engines. And you're seeing linear optical distortions in much the same way as is being caused by the, in this case, the Falcon Heavy vehicle itself, but it's being caused by particulate matter in the exhaust. And you're seeing how it's turning the backdrop of the sun into this discontinuous, shimmery mess. And it is absolutely phenomenal to see all of this. But we're seeing it still from rocket flight itself. It's evident on Falcon Heavy. I have not personally observed it from the tracking camera footage of Falcon 9, but I'm sure it's happening there if it's happening on Falcon Heavy. And of course, we demonstrated that it also used to happen on the Space Shuttle via STS-104 and this paper from the Marshall Space Flight Center published in 2011 by NASA. So it is something that's real, and if you happen to notice this, either in your rewatch of Falcon Heavy's launch or in future SpaceX or other space launch providers' endeavors, if you see this in their launch coverage, no, you're not going crazy, and no, nothing is wrong with the cameras. You're seeing something that is very real and something that has some very cool explanations as to what's happening and how it's happening. So I hope that this was interesting, if not informative for you. And I do have to thank you all very much for persevering with me for these 47 nigh on minutes. And I hope you got something out of this one. As always, Ferrari Man 601 saying thank you very much for watching, and of course, we will see you soon.